Welcome back. On behalf of Forge College, I'm super excited to dive into today's explainer. Grab your dark green technical pens and let's start sketching on this beige blueprint paper. Because today, we're going into a literal engineering drafting session for building scalable Solana skyscrapers. We're tackling the foundations of program architecture. If you've ever wondered how top-tier developers structure their code to handle massive, high-frequency loads without the whole thing crumbling into a congested network mess, well, you're in the right place. All right, here's our master blueprint for today. First, from bricks to blueprints. Second, 3 core architectural questions. Third, the modular program skeleton. Fourth, the architect's design workflow. And finally, a final inspection. Let's get right into it. So before we start pouring the concrete for our skyscraper, we've got to talk about the raw materials. In our previous lesson, implementing advanced data structures and performance checks, we got our hands dirty with compact memory layouts and safe concurrency under Rust's ownership model. And listen, those data structures are absolutely phenomenal bricks. But here's the funny thing about bricks. If you just stack a bunch of them randomly in a pile, you don't magically get a skyscraper, right? You just get a really heavy, really expensive pile of clay. Ask yourself right now, is your code currently a skyscraper, or is it just a pile of bricks? Because to build something that truly scales to millions of users, you absolutely need a blueprint. Well, what exactly is that blueprint? That's what program architecture actually is. It's defined as the deliberate structural decisions mapping your application's requirements to runtime primitives, meaning your accounts, instructions, and programs. Simply put, this is the exact moment where your low-level choices about memory management suddenly become massive system-level properties. If you're building a decentralized exchange, this is where you lock in whether your app can handle 100 swaps a second or 10,000. It's how we guarantee our application behaves predictably when the whole world is trying to click your buttons at the exact same time. To draw up this architecture, we have to ask 3 really specific questions. Number 1, where does state live? Think of accounts as the individual rooms in our building. You have to decide on the granularity and layout of those rooms. Mechanically, the Solana runtime locks accounts per transaction, so you absolutely want to group frequently updated fields together in the same account, keeping your hot paths, like active trading balances, totally separate from cold data, like static protocol settings. It's kind of like putting your kitchen right next to the dining room. It just makes serving dinner way faster and drastically reduces the bottleneck when everyone is trying to eat at once. Question number 2, who owns it? If accounts are the rooms, ownership is the locks on the doors. This maps directly to your security and upgrade patterns. By clearly scoping authority accounts and utilizing program-derived addresses, PDAs for short, you're basically setting up cryptographic algorithmic locks. There are no private keys here. It's purely programmatic logic unilaterally enforcing your program's rules. For example, given an automated market maker pool the sole authority to own and transfer its tokens. That simplifies permission checks tremendously, because the program never has to ask for external cooperation to know its state is completely secure. And the final question of the big 3, how do instructions access it? If the accounts are rooms and the PDAs are locks, your cross-program invocations, or CPIs, are the hallways connecting different buildings. Let's say you need to call the SPL token program to transfer funds. Just like walking down a really long hallway, I literally cannot stress this enough. Every single CPI adds compute overhead and extra account metadata handling. If you design an API that forces your users to sprint through a sprawling maze of hallways just to do one simple action, your transaction compute costs are going to go straight through the roof. Which brings us to a huge debate in Web3 development, monolithic versus sharded accounts. Think of a monolithic account like stuffing your entire extended family into a single tiny studio apartment. The upside? Lower CPI per operation, because hey, everyone is right there in the same room. The downside? Extreme contention. Nobody can move without elbowing someone else, and your transactions just bottleneck. Sharded accounts are the exact opposite. Everyone gets their own separate house. You get incredible parallelism, thousands of users acting at the exact same time without blocking each other. But the trade-off? Now you're paying the HOA rent fees for all those houses, and there's significantly more bookkeeping to track exactly who lives where. So how do we divide things up? We use program boundaries. A program boundary defines the strict rules and contracts a program enforces entirely on its own. Now, modularity, splitting your project into multiple distinct programs, sounds awesome because it reduces our cognitive load as developers. We love tidy little boxes. But remember those hallways we just talked about? Every boundary introduces CPI overhead. So setting these boundaries is a constant, deliberate trade-off between how simple the code is to read for you at your desk and how fast and cheaply it actually runs out there on mainnet. When we look at transaction flow, we constantly contrast small, self-contained instructions against heavy cross-program invocations. For high-frequency transactions, you absolutely want a minimal footprint. You want instructions that touch only the specifically required accounts, do their job, and get out. If your instruction is dragging along 10 different accounts and bouncing between 3 different programs just to execute one thing, you're massively increasing your compute limit and practically begging for a network traffic jam. When you're building for scale, less is absolutely more. Let's look at what this actually looks like in code. Here's a beautifully clean, idiomatic Rust skeleton. You've got your imports handling compact Borscht serialization, which means your data is packed down as tightly as mathematically possible. You've got an instruction enum that completely centralizes your API. Then process instruction acts as your main entry point, using a super efficient match-based dispatch to route traffic. Finally, you isolate your actual business logic into a dedicated handlers module. Setting it up this way keeps everything cheap, modular, and incredibly predictable for the runtime. And when you're writing those handlers, here is your golden rule. When you absolutely have to use CPIs, you must follow this strict pattern. Encapsulate your validation, pack and unpack minimally, and meticulously document the access list for each handler. By encapsulating validation, you cut out duplicate security checks across your code, which saves precious compute units. Callers can batch their instructions correctly, and you lock in rock-solid, predictable compute costs. That predictability is exactly what stops your app from crashing when it suddenly goes viral. Okay, let's turn this into a daily practice with the architect's design workflow. It's a 5-step repeatable checklist to transition your ideas from theory into measurable engineering. Step 1, map your access patterns to find the hot data. Step 2, choose your account granularity strictly based on that map. Step 3, define ownership in your PDAs right from the start. Step 4, optimize your serialization. Pack those integers tight to save space. And step 5, benchmark and iterate. Never guess when you can measure. Speaking of measuring, good architecture turns subjective arguments like, does this code look pretty, into concrete, actionable data. You need to obsess over 3 measurable signals: the compute units per transaction, the number of account locks occurring, and your average serialization size. Listen, if a structural change to your program doesn't directly improve at least one of these 3 signals for your specific workload, it's not an architectural improvement. You're literally just rearranging the furniture in the living room. All right, time for the final inspection on our blueprints. If you only remember 3 things today, make it these. First, always align your account layout with your actual access patterns. Co-locate that hot data. Second, treat every single program boundary as a deliberate, costly trade-off. Don't just split programs for the sake of it. And third, design for minimal, predictable instructions. Stick to these principles, and your Solana programs will behave with ironclad predictability even under the heaviest network loads. And that wraps up today's drafting session. In our next lesson, we're taking all of this and getting our hands dirty applying concrete scalability solutions, implementing sharding and parallel transaction patterns. Your homework before then, prep an access map of 3 hot operations in your own code so you can measure the improvements directly. Thank you so much for hanging out with me on behalf of Forge College. Be sure to check out forge.college to dive deeper into this subject and discover even more Web3 topics. Let me leave you with this thought. When 1 million users suddenly rush the doors of your application tomorrow, is your skyscraper gonna stand tall, or will the foundation crack under the weight? Catch you next time.